Welcome back. Today we'll continue our discussion on compressibility corrections and compressibility effects on turbulent flow for the purposes of turbulence modeling. Just to review, equations that we need to close, which we developed before, are the Favre average Reynolds stress and averaged equations. So 843 here is the Favre average Reynolds stress equation for Reynolds stress. And here are the closure correlations apparent in the model. Here. Next, there's the typical continuity equation, momentum equation, energy equation, TKE equation, terminal kinetic energy, and a gas law. Of course, for high-speed flow, it's very typical to use something other than ideal gas, and we have our typical definitions of total energy and enthalpy. So let's just take a look at these equations for a second for your own purposes, and we'll make some general notes about closures, and then show some sort of established closures that most people in the community know about. Just take a second to look at them again. Pause if you need to. Okay. So equations 843 to 852, which we just showed on the previous page, contain the effects of compressibility mainly through correlations that need to be modeled and closed with coefficients and auxiliary functions for how the density fluctuations alter the turbulent flow. So all but the turbulent stress models, the diffusivity type closure approximations must be postulated for these Favre average, Reynolds stress tensor, and heat flux vector and equations. So the transport models and closures must be postulated. This is a very difficult task. And depending on the type of the turbulence model that we choose to use, additional closure approximations may be needed to close the entire system which define the model. So closure approximations define the model, and it's dependent on our choice. So we're going to try and review some of the most common ones used for high-speed compressible flows. And it is true that measurements for incompressible flows and additional complexities for compressible flows are definitely less available. So there's less data available for modeling in terms of experiment or DNS. So that adds to the difficulty. And therefore, the modeling of the compressibility effects is always in a state of development, even today. Therefore, the closure approximations that we're going to discuss are generally those that are most popular. So before we focus on particular closures, we'll try and cite some important guidelines for these closures. And we'll try and always look for simple and, if lucky, elegant closures. And these are ones that are often more accepted by the community because they're easier to program, and maybe in the spirit of Pauli Dirac, they might be more correct. So there's a few things we look for in these particular closures. One is that they should approach the limiting form of, say, incompressibility for lower Mach numbers. So as flow becomes incompressible, lower speed, that we recover, say, density independent predictions. Second, the closure should absolutely be written in tensor form. Advantages, and that's good to have it be accepted by the community. And all the closures should be dimensionally correct. And Galilean invariant, meaning that when we rotate them, we're getting the same formulation and results. Now, generally in practice, the Galilean invariants can be ignored by some people, especially for compressible flows. But we would reject those models because that is actually a fundamental feature of the original Navier-Stokes equations. And we would want to preserve that so that we have physical results. So we must preserve Galilean invariants for mathematical consistency and physical results. Very important. And I think a lot of people overlook this important step. Also be careful with some variables, like say the total enthalpy, include terms like turbulent kinetic energy and can be shown to be Galilean invariant. And using these types of dependent variables requires caution. These are good notes for people going into turbulence modeling. So now that we made these little notes, let's look at each term by term and just talk about what the most popular models might be. The first one we might model is the Reynolds stress tensor. And typically 0, 1, and 2 equation models, of course, use Boussinesq approximations. And those are using ideal viscosity. So for this type of model, we might model the Reynolds stress tensor for these high-speed compressible flows as, say, something like 2 times the viscosity, eddy viscosity, times Sij, minus 1/3 of partial UK bar partial xk delta ij, minus 2/3 of rho k delta ij, which is the Kronecker delta function. Oh, and excuse me, there's no parenthesis there. So that's the most common formulation. And, oops, I think I need a bar across my row here. This is an average quantity. Let's look at the turbulent flux vector for heat transfer. And usually this is a common closure approximation for, say, Qt sub j. And we try and use what Reynolds did in 1874, but for high-speed compressible flows. And we'll assume that it's proportional to the mean temperature gradient. So in the compressible case, we might write rho uj prime prime h prime prime bar, which is equal to negative mu t c sub p all over turbulent Prandtl number times partial t tilde partial xj minus, which is equal to mu t over pr t times partial h tilde partial xj. And this is the turbulent Prandtl number, as I just mentioned. And this works well for flows without particular shocks. And in studies with shocks, this is not a good assumption. But the most common values for PRT is about 0.89 or 90. And the heat transfer predictions can usually be improved by, say, varying PRT through the boundary layer. So there are variable PRT models, which is the subject of current research in 2022. And in the rest of the flow, it might be on the order of, say, 0.5, say in like a shear layer or a free stream. So that's the most common turbulent heat flux vector approximation. Now what about molecular diffusion and turbulent transport? Well, If a zero equation model is used, then we have a term 2/3 rho k Kronecker delta function will contribute to equation 853, and that can often be ignored and seen as molecular diffusion stress times ui double prime, or turbulent transport, and these appear in the mean energy equation. Now this allows for a good approximation with flows where the Mach numbers are, say, up to supersonic ranges, because, say, rho bar k is much less than production. And therefore, turbulent kinetic energy is less than static enthalpy, mass averaged. And this is good for most just non-hypersonic flows. At hypersonic speeds, it's absolutely possible to have these inequalities be opposite. Rho bar k is much greater than production in certain cases. And in these cases, we need to ensure that there's energy conservation of total energy, which includes k, and the closure should approximate this. And generally in one equation, two equation, and Reynolds stress models, we will try and generalize these flows with low speed closure approximations for the molecular diffusion and turbulent transport terms. The most common closure you'll see is viscosity plus mu t all over some k times partial k partial xj. So we've taken our unknowns and written them into known quantities of viscosity plus an eddy viscosity times the derivative, spatial derivative of turbulent kinetic energy. Let's look at the dilatation dissipation next. And someone might say, well, what is dilatation dissipation? Well, to understand it, you need to examine the turbulent energy dissipation rate. And if you go back and look at equation 8.42 of these slide deck lectures or notes, you'll see that rho times dissipation goes as TEJI partial UI double prime partial XJ bar. And in terms of instantaneous strain rate tensor Sij, we can write rho E as barred correlation mu 2SJI Sij double prime minus 2/3 UK UI double prime. So if we make an assumption that the correlation between the velocity gradient fluctuations and turbulent viscosity fluctuations are small, then we can rewrite rho E as a Favre-Aldrich kinematic viscosity times 2 rho SJI Sij double primes bar minus 2/3 of rho UK double prime UI double prime. This. And we can then rewrite the same in terms of fluctuating vorticity. And then that might be rho or nu bar times rho omega I double prime bar plus 2 rho uj double prime uji double prime bar minus 2/3 of rho ui double prime double prime bar in bracket. You can also that uj double prime uji double prime goes as a square of ui double prime. And this is true for homogeneous turbulence, and is definitely a good approximation for a high Reynolds number in homogeneous turbulence. And we might, as a model, and we can try and conclude that the dissipation might go as rho bar s plus rho bar epsilon d, epsilon s. And what are those definitions? Well, they go as, I'm going to zoom in here, nu bar rho omega I double prime bar, and for epsilon d 4/3 of mu of rho ui double prime bar. Wow. So a few notes about these equations. We have quickly shown that for the compressible dissipation rate, we can write them in terms of fluctuating vorticity and divergence of the fluctuating velocity. could also write these as fluctuating velocity as summations of divergence-free and curl-free components. And at high Reynolds number, these components are typically uncorrelated, as in equation 859 here. And epsilon we call the solenoidal dissipation. And epsilon d is the dilatation dissipation. And epsilon d is really present for compressible flows. Now, multiple DNS studies in the late 90s showed that the dilatation dissipation should typically be a function of turbulent Mach number, which would go as 2k all over, say, a squared, where a is the speed of sound, and k, of course, is turbulent kinetic energy. So, in their studies, they tried to argue that k epsilon equations could be replaced by this set here, where we include the solenoidal and dissipation viscosity, dissipation explicitly. And they have some new closure coefficients, like CO2. Here, only the dissipation terms are shown in equation 863 and 864, and no other changes are made to the rest of the equations. And it's postulated by those authors in those papers that epsilon is unaffected by compressibility, so it would remain. And therefore, the dilatation dissipation would be assumed to be proportional to epsilon s. And so they've related them in this particular function 865, where chi sup star is a closure coefficient and fmt is a function of mt. And they prescribed and give ideas what this function might be based on their DNS experiments. Now, both of them arrived independently at the same formulation, and their postulates, however, are very, very different, which is very interesting. For example, Sarkar and his co-investigators postulated that epsilon d varies on a fast compressibility timescale relative to epsilon s. They also conclude that the dilatation dissipation increases with MT in a monotonic matter. Zeeman and his co-investigators viewed the existence of eddy shocklets, which are principally responsible for the dilatation dissipation. And their analysis predicts that there's some sort of threshold below which dilatation dissipation is negligible. This viewpoint might be flawed for reasons which are maybe beyond the scope of this lecture. But further DNS results of compressible shear layers in 95 by multiple authors for channel flows and for mixing layers showed that the dilatation dissipation is small or negligible even in the presence of eddy shocklets, which sort of might neglect the theory of Zaman and his co-workers. And these channel flow results are consistent with the fact that compressibility corrections may not be needed for boundary layer flows. And the DNS results also show insignificant pressure dilatation, which we'll talk about next. Anyway, the dilatation corrections shown by Zeeman and Sarkar can, with particular calibration of the coefficients and auxiliary functions, might match measurement data of mixing layers with care. And they can also be formulated to find good results for at least non-hypersonic boundary layers where MT is lower and say that turbulent Mach number isn't that large. And at the end of the day, they're still seen as empirical corrections rather than true models, but they are still remaining some of the more popular ones today. Let's next look at the pressure diffusion and pressure dilatation terms. There's generally a lack of information regarding the diffusion by pressure fluctuations, even in incompressible flows. Which is probably worrying for compressible flows. So that means that even less is known about these particular triple product correlations in high-speed flows. Now, we're lucky in some sense. There's some fundamentally different role that pressure plays in compressible flows relative to, say, incompressible flows at low speed. And therefore, we might suspect that ignoring pressure diffusion and pressure dilatation might lead to error. Thankfully, with DNS results, we can see that dilatation, dissipation, and these terms are very small for both mixing layers and boundary layers. DNS suggests terms are small, and that's good, especially when we don't know much about them. So for dilatation, dissipation, we might see that early homogeneous strain simulations might have been misleading. In the 90s, Zeeman and his collaborators examined pressure dilatation in large flows with large ratios of turbulent kinetic production to dissipation, and typically of strong strain initially isotropic flows. In thinner shear layers, the production and dissipation are actually in roughly the same order as the pressure dilatation, which is small. And this has nothing to do with really Reynolds number. It's determined more by the eddy size and mean square dilatation, and it may not have much effect with viscosity. So models for pressure terms, in terms of improving predictions, are generally rather ad hoc or empirical in nature, and definitely do not represent the true physics of compressible turbulent flows. Now, new particular proposals in the last many years have tried to get generally accepted models. And what would those be? Probably one of the most popular is by Sarkar in 1992, and they proposed that the pressure dilatation can be approximated as alpha 2 times rho bar tau ij partial u tilde I partial xj mt plus alpha 3 rho bar rho epsilon mt squared. Let me just make that correction. There we go. And once again, mt is turbulent Mach number. And alpha 2 and alpha 3, here and here, are closure coefficients. And generally, they're set as 0.15, alpha 3 of 0.20. And these were calibrated by Sarkar against a number of DNS flows for mixing layers and boundary layers. Another term is the pressure work term, which is ui double prime p, ui double prime pj plus uj double prime pi for the stress transport models. And these, of course, arise because the time averaging of ui double prime does not vanish as we're doing Favre averaging. And generally, this is proportional to the density-velocity correlation. And this really illustrates how the Favre averaging does not completely eliminate the need to know how these fluctuating properties are correlated. A number of interesting papers were written on this particular term. Wilcox and Elber in 1972 showed an empirical model for the term that improves two equation model predictions for hypersonic flows. O, in 1974, looked at a closure approximation postulating the existence of eddy shocks and simulated compressible mixing layers with a one equation model. So I'll make notes of these. O in 1974. Unfortunately, neither of these models really work well where air flows with mean velocity in a manner that violates Galilean invariance of the Navier-Stokes equations. Today, the most accepted way to model ui double prime in this term is by Zeeman in 1993 and Ristorcelli in 1993, and they said that it should go as mtk over rho bar epsilon tau ij partial rho bar partial xj. And measurements actually show that this model is essentially non-existent, and we can try and say at least that it's dimensionally correct and does not violate Galilean invariance.